Today we're going to look at section 5.7, Factors and Zeros of Polynomials. Our objectives are to be able to use the graphing calculator to find rational zeros, to be able to find all factors, linear factors, zeros, and x-intercepts of a given polynomial, and to be able to write a polynomial, assuming it has a lead coefficient of 1 from given zeros. To start this, to help us out, we want to kind of look at what the fundamental theorem of algebra tells us. And simply put, it says if we have a polynomial of degree n, we'll have n zeros, roots, or solutions, and just different names for the same thing. So that means that if I have, say, a degree of x to the 6 plus, say, 5x cubed plus 1, say that is my polynomial or my function. This has a degree of 6. That means that when I'm solving, I should get 6 solutions, which is sometimes also called roots or sometimes also called zeros of the polynomial. Okay, so this will help you know how many answers you should have. So here are the steps, and they're already typed down in your notes for you, that we need to use to find zeros on a graphing calculator. And I'm going to go through these steps for each of our 3 examples, but now at least you have a reference for it. So my goal on this one is to find all the factors, linear factors, zeros, and x-intercepts of this function. So the first thing we actually want to do is to type it into our y equals, and I've actually already done that to save a little bit of time. So if we go to y equals, disregard the other functions, I'm just going to look at y1. What I want to do is I'm going to hit zoom 6. If you remember, that's our standard graph, our 10 by 10. And normally you would have to look all over, you'd have to expand your window. But for our problems in class, you can keep it at this window to help you find your rational zeros. So it graphed the polynomial, and it's kind of crazy looking because we have a small graph. But remember, what I'm trying to find are all these, and the easiest thing to find from a graph is our zeros, or what we call x-intercepts. So remember, all x-intercepts are zeros, but not all zeros are x-intercepts. So if I look at the graph, it looks like there's 1, 2, 3, 4 x-intercepts. So what I'm going to do is there's 2 ways to find them. We practiced hitting second trace and using the zero function. That takes a little bit longer. Since I want to find rational zeros, which are numbers that can be written as a fraction, I'm actually going to go, and we're actually finding the integer ones, more specifically in our calculator. I'm going to hit second graph, and that takes me to the table. And what it does, it gives me all the points on the graph in integer values. Now, hopefully you're going to, if you scan, you can get to 0, 35, 148, 227. If this is not what you see on your calculator, okay, what I want you to do is hit second window. That gets you the table set up. So you can do table start at 0. Okay, this is the change in the table. So that tells the table I'm going to go by ones, and you want independent, dependent always to be on auto. Okay, but if you see what I have already, you probably don't have to worry about this. So I'm going to go back to my table. Now, if I look at my graph, it looks like there was 2 negative x-intercepts, 2 positive x-intercepts. So I'm going to go to my table, and I know I'm in the standard, so I'm from negative 10 to positive 10. I'm just going to go to negative 10 and start to look. Do I have any x-intercepts? So if I kind of scroll down, nothing. Oh, here's one. I have 1 x-intercept at negative 1, 0. Okay, and if I keep going, I have another x-intercept at 5, 0. And I'm just going to go to positive 10 because that's what my graph goes through. So right now, I know I have an x-intercept at negative 1, 0 and at 5, 0. Which means if it's an x-intercept, that means it's also a 0. But because this is x to the 4th power, I know I should have 4 total 0 answers. But I only have 2. So that means I'm missing 2 other answers. But what else can I do with this information? I know that if I have a 0 at negative 1, that means I have a factor at x plus 1. Now this is linear because this, if I graph this, this would be the equation of line. So that factor is also a linear factor. A lot of our factors are linear, but we will get to some examples where they're non-linear. And because I have 5 as a 0, I know that x minus 5 was my factor. Again, if I graph that, it would be a line because it's x to the 1st power. So that means x minus 5 not only is a factor, but it's more specifically a linear factor. So I got almost all of the work done. I got half of the work done just by looking at my calculator. So how do I find the rest? Well, that's when our division comes into play. And synthetic division tends to be a little bit easier for students, especially when we have our linear factors. So what I'm going to do is some synthetic division. It does not matter which 0 you use first. I'm going to choose to use negative 1. So I'm going to put negative 1 on the outside. Okay, I'm going to draw my little bracket and then put all my values. X to the 4th, x cubes, x squareds, my x's, and then my numbers. Now I'm just going to go through. I'm always going to drop down this first number, and then I'm just going to fill it in. Multiply, I get -1. I add, I get -5. Multiply, I get 5. Add, I get -7. Multiply, I get 7. Add, I get 35. Multiply, I get -35. And when I add, I get 0. You have to get 0 here. If you don't get 0, then you messed up your algebra or you read something wrong from your calculator, because we know it's a 0, and if you remember from our remainder theorem, by definition, if it's a 0, that means it has a remainder of 0. So now I just took my problem and I actually made it a little bit smaller. So I could try to factor this by hand, but I want to show you guys sometimes called a nesting synthetic division, but I'm going to do synthetic division twice. I also have another 0, so I could try to factor this by hand, but why not make this problem smaller, which usually makes it easier to factor. So I'm going to show you how we're going to do this. We're not going to rewrite this, and the biggest problem that students make is they go back and do synthetic division with our original problem. Our goal is to make this problem smaller and smaller and smaller. So now that I have this, I'm going to just draw my synthetic box again, but now I'm going to use 5 as my 0. So I'm going to drop down my lead number, my 1, and then I'm going to multiply through again. Let's use a different color. So 5 times 1 is 5. Add, I get 0. 5 times 0 is 0. Add, I get -7. 5 times -7 is -35. And when I add that, I get a remainder of 0. Oh, that guy's winking at you. Now, the other reason I put a smiley face, 1, I like smiley faces, and 2, is I don't want to think this is a 0 and think it's another column that I need to do work for. So by putting a smiley face, hopefully that reminds me that, you know what, this column doesn't exist in my new synthetic division, so I can stop. I don't have any more zeros to try, so let me look at this. Okay, and if you remember when we did it originally, synthetic division in our 5.5b section, I talked about this is my remainder, these are my numbers, these are my x's, and then these would be my x squareds. This is a lot easier method than trying to remember, well, this was my x to the 4th column, but then it became an x to the 3rd column, now it's an x squared column. If you just do this, it makes it a lot easier. So I now know my last little factor is x squared minus 7. If there's a 0, you don't have to write it. So this is my factor, because if you take a number and keep dividing it by numbers that go into it, okay, this would be my last factor. So ask yourself, can you factor this anymore? Well, there's no GCF, and it's a subtraction, but this isn't a difference of 2 squares or a difference of 2 cubes, so this must be my last part. So if I write this up here, x squared minus 7. Now that is not a linear factor because it's x squared. If I actually graph this, I would get the graph of a parabola. So I can't write that down here. But we are going to have to end up having 4 linear factors because we're going to have 4 zeros. So I'm going to get to this part in a second. If this is a factor, that means that if I set this equal to 0 and solve, I should get another 0. So I'm going to get x squared equals 7. X equals, if I take the square root of both sides, plus or minus the square root of 7. This is actually 2 separate answers. Those are my zeros. I get the square root of 7 and the negative square root of 7. Okay. Those can actually be written as x-intercepts because they're real. So I get an x-intercept at root 7, comma 0, and one at negative root 7, comma 0. And if you want to just write that as plus or minus root 7, 0, you're more than welcome to. So how would I write linear factors? Well, if I know these are my zeros, I know I get a linear factor at x, and I'm just going to save space here, plus or minus root 7. X minus root 7 and x plus root 7. Those are linear because if I graph them, I would get lines. And that's the difference between factors and linear factors. And I know I should have 4 answers because my degree is 4. Let's look at the next example. Okay. Again, we're going to go to y equals. Let the calculator turn on. Going to go to y equals. Okay. But this time, since I already have it typed in, you're going to want to clear out your equations. Okay. And then we're going to graph our second one. Again, we're going to hit zoom 6. It should already be there, but let's do this to help out. And now this time, it appears to have 1, 2, 3 x-intercepts. Well, if I look at my original problem, I know this has a degree of 3, which means I should have 3 answers. So that tells me all 3 of my answers are going to be real, and they all happen to be x-intercepts. But I want to know which ones these are. So I'm going to go into the table, And again, anywhere from negative 10 to positive 10. So there's my positive 10, no zeros, but here's an x-intercept at 4, 0. And let's see if there's any more. If I keep scrolling through, oh, I have an x-intercept at negative 4, 0. And nothing else. So those are my only nice kind of pretty answers. So I know I have one at 4, 0 and one at negative 4, 0. So I only have to find one more answer because I know I have a 0 at 4 and a 0 at negative 4. Okay, so I only need to find one more because I know I have 3 answers. Okay, so now I'm going to do synthetic division. I'm going to use 4 first and then draw my bar. So I have 2x cubes, negative 1x squared, negative 32x's, and 16 for my number. I'm going to drop down the 2, and now multiply. 4 times 2 is 8. I add, I get 7. 4 times 7 is 28. I add, I get negative 4. 4 times negative 4 is negative 16. And I get a 0, which is exactly what I should get, because I know from my calculator that that's a 0. Now I could try to factor this by hand, but why not just do the easy synthetic division again? I'm going to drop down to 2. Okay. This time I'm going to use negative 4. And then I'm going to multiply. Negative 4 times 2 is negative 8. I add, I get negative 1. Negative 4 and negative 1 is a positive 4. And again, I get a 0, which is exactly what I should get. Here's my remainders, my numbers, and my x's. So if I write this out, I get 2x minus 1. Now you look, you can't factor it anymore. And this is actually linear because it's x to the first power. So I'm going to do a couple things out of order, but I have 2x minus 1, that's my last factor, and I know this equals 0. Well, if I solve, I get 2x equals 1, x equals 1/2. So this is my last 0 or solution is 1/2. But I can write that as 1/2 comma 0. Sorry about that, 1/2 comma 0. Because I know when I put 0 in for my solution, I get 1/2. How do these work as zeros? Well, I know I have a 0 of 4, so my factor is x minus 4, and that's linear, so I could write that in both places. I know when I have a 0 of x minus 4, that meant my factor was x plus 4, and that is also linear. And my last factor was 2x minus 1. If I graph that, I get a line. So I don't have to do any work like I did in the last one. 2x minus 1 is my last linear factor. Let's go on to our last example. So now this one, if I look, is x to the 5th power. That means I'm going to have 5 solutions or 5 zeros. So I'm going to go back to my y equals. Okay, I already have it typed in, but you're going to want to clear out y1. Okay, hit graph after you hit your second 0. Or your second, your zoom 6. Now if I look, it looks like it only hits the x-axis 1, 2 times. But I know I have 5 solutions, so they must not all be x-intercepts. So let's go back into the table and see which numbers are x-intercepts. So if I scroll through, I see that negative 2, 0 is an x-intercept, and 1, 0. So negative 2, 0 and 1, 0 are my x-intercepts, and there was only 2 things I saw anyways, so I know I have negative 2, 0 and 1, 0. Okay, which means that negative 2 is a 0 and 1 is a 0. I know that I get a linear factor at x plus 2 and at x minus 1. Okay, and those are also factors. Okay, the only time there's a distinction between these is if you have an x with an exponent other than a positive 1. So now I still need to find my other 3 missing terms. So let's just start here with a negative 2 and go through the synthetic division. So 1, 1, 2, negative 12, and 8. Oh, but be careful. We need a placeholder. So I'm going to erase this real fast. Should be 1, 0, 1, 2, negative 12, and 8. Okay, even with this, we need to put placeholders. So to the 5th, to the 4th, 3rd, 2nd, 1st, and numbers. The easy thing to think about is if you have x to the 5th, you should have 6 numbers here. If you had x to the 4th, there should be 5. You always have 1 extra number, then the degree to count for that number at the end. So I'm going to drop down the 1. Negative 2 times 1 is negative 2. Add, I get negative 2. Multiply, you get 4. Add, we get 5. multiply negative 10, add negative 8, multiply positive 16, add 4, multiply, we get a negative 8, and things are all connecting. We get 0 for a remainder. Okay, but I know I have another 0, so I'm just going to keep breaking this down smaller and smaller. Now I'm going to use the 0, 1. Okay, again, I'm going to multiply. 1 times 1 is 1. Add, I get negative 1. Multiply, I get negative 1. Add, you get 4. Multiply, you get 4. Add, you get negative 4. Multiply, you get negative 4. And again, there's our 0. Now we have a couple of choices. We could factor this. Okay, and I just want to show you that quickly, just in case you got to this point and got stuck. This would be, I'll write it up here, okay, x cubed minus x squared plus 4x minus 4. Again, remainder number x squared, x cubed. Now this is 4 terms. Now we know how to factor this because we know factor by grouping. But instead of doing that, let me just show you something on the graph that people might not have noticed. Remember when we graphed in 5.2 polynomials? Right here at this 0, okay, I'm going to zoom into that just a little bit so you can see. I'm going to go from 0 to, let's go to 3. If we look at the graph right here, at that 0, it bounced off of it right there at that positive 1. Well, if you guys remember what we did in 5.2, if it bounces off of it, that means it's a double root. That means it doesn't happen just once, it actually happens twice. So, again, I'm just going to write my x-intercept once, but I actually have that 0 twice. So that means that I can do synthetic division with that number 2 times. Now you could factor this, you could stop, but sometimes the problems are too hard to factor, and it's always nice to make it smaller. So now what I'm going to do is going to go all over again and use 1 twice because it's a double root. So I multiply, I get 1, add, I get 0. Multiply, I get 0, add, I get 4, multiply, I get 4, and again I get a 0. Okay, again, this is my remainder, my numbers, my x's, and my x squareds. So if I factor that down, because I know I have, this is a 0, I know I have x minus 1 twice. Now I could just write squared, or you could write it twice, it's up to you. Okay, and again, if you want to write the x-intercept twice, normally we don't write it twice, but just so you can see that we have 5, kind of x-intercepts. Well, in this case, 2 x-intercepts. I'll just take that off just so you don't get confused by it. So now that I have this, okay, I could have factored this, but I also could have just done synthetic division again and then got x squared plus 4. Now, this does not factor anymore, okay, because it's a sum of 2 squares. We only have difference of 2 squares. So that's my last factor. 1, 2, 3. We only have 4 factors, okay, because we normally say this is not factorable. But I need to have 5 linear factors. So what do we get when we actually set this equal to 0 and solve? Well, I'm going to get x squared equals negative 4. And when I take the square root of both sides, I get x equals plus or minus the square root of negative 4. Hopefully you remember what this is. When you take the square root of a negative, that means it's an imaginary answer. And the square root of positive 4 is 2. So this is actually plus or minus 2i. You cannot write this as an x-intercept because we don't have imaginary x-intercepts. So I'm going to put plus or minus 2i right there. Now how would I write this as a linear factor? I know it's kind of small up here, but this is just going to be x plus 2i and x minus 2i. Those would be my linear factors. So whenever you have 5 solutions, you should end up with 5 linear factors. You might not always get 5 actual factors. Now, if you remember what we did in 5.2, what would be the degree of this problem? Well, 1, 2, 3, 4, 5 are our exponents of x, and that's why we have a degree of 5. And again, I can't write these as x-intercepts because they're not real. So that's the different type of questions you're going to be asked in class. The other type of question I'm going to ask you is kind of work backwards. If we know that these are given zeros, can we go back and work at the polynomial? Well, I don't know if you noticed, but in the last problem, if I have a 0 of 2i, anytime I have an irrational answer, because again, remember I is the square root of negative 1, that's an irrational number. I won't just get the positive. You will always get the positive and the negative. So if I just show you an imaginary number, you will always have its conjugate. So if you remember, this is 0 plus 2i, so this would be 0 minus 2i. They will both exist. Okay. So how do I go back and write the polynomial? You have a couple of choices. I could If this is a 0, I know my factor is x minus 5. If that's a 0, I know it's x minus 2i, and this would be x plus 2i. What we would have to do is distribute, which we did in 5.3, and expand this. So I'm going to kind of go through this quickly. I'm actually going to distribute this first, which gets me x squared plus 4. Okay, we can kind of see that from our last problem. And then if I distribute here, I'm going to get x cubed plus 4x minus 5x squared minus 20. Now we usually don't write it that way. We always write it in descending order. So this would be x cubed minus 5x squared plus 4x minus 20. And again, we're writing a polynomial, so you could write f of x, or p of x if you want to use for polynomial, equals that. That's how we work backwards. Again, this is an irrational number, so we won't always just get root 3. We're going to get a negative root 3 as well, because to get a root 3, we'd have had to take a plus or minus of both sides, and that's our positive and our negative. So what would you do in this case? X minus 1, x minus 2, x minus root 3, and if it's a minus root 3, it'd be x plus root 3. Okay, you could do a couple different things. This becomes x squared minus 3x plus 2 if I was to FOIL and distribute that out in combined like terms. These two become an x squared. Okay, let's see what we get. We're going to get x squared. The middle terms go away, and then we're just going to get minus 3. Okay, because this is a conjugate. Okay, when you multiply conjugates, if you remember what we did earlier, you get the first term squared and the second term squared. So x squared minus, because positive and negative, 3. And if you remember from 5.3, now we would distribute. I'd get x to the 4th minus 3x squared. If I multiply this, I'm going to get a negative 3x cubed plus 9x. And if I distribute the last one, I'm going to get a 2x squared minus 6. Okay, so I just did that instead of writing it out. So if I wrote this in order, I have x to the 4th, because that's the only one I have. If I look at my x cubes, I only have 1, negative 3x cubed. If I look at my x squareds, I have a negative 3 and a positive 2, so that's negative x squared. And I only have 9x and a negative 6. Again, this is our function, or our polynomial, however you want to write it out, and that would be it expanded. If I wrote these out as factors, it would get really complicated. I'd have x minus this quantity, and then x minus this quantity, just like I did in last problems, and it gets really, really hard to distribute that out. Instead, I like the strategy of kind of working backwards. If I know these are my zeros, I know at some point I got an answer of x equals, and I'll combine those as 1 plus or minus 5i. I'm going to actually take this and do the algebra backwards to see what I started with. So the first thing we would have done to get, if the step right before this, it was x minus 1 equals plus or minus 5i. Okay, because then I would have added 1 to both sides to get my final answer. The step before this would have had x minus 1 squared equal to 5i squared. Because what I would have done is taken the square root of both sides to get this answer. And if we take the square root of this, we get plus or minus 5i. The step before this would have been x squared minus 2x plus 1, because this would have been factored. And this would have looked like 25, just so you remember what this is, 25i squared. Well, I squared is negative 1, so this would have been a negative 25 the step before. And then the step before that would have been x squared minus 2x plus 26 equals 0. So this is what I was trying to solve. And if I know this equals 0, when this is equal to 0, it gives me my answer. I know this is actually one of the parts of my polynomial. Let's do the same thing over here. I knew x was equal to 4 plus or minus root 2. The step before that would have been x minus 4 equals plus or minus root 2. The step before that would have been x minus 4 squared equals, okay, root 2 squared. The step before that would have been x squared minus 8x plus 16 equal to 2. And then the step before that would have been x squared minus 8x plus 14 equals 0. Because this is basically just completing the square. That's where all these answers come from. We would have moved all the numbers over and completed the square and got this final answer. So what that tells me is this is my other part. So if I took this times this and combine all my like terms, I would get my polynomial. And I'm not going to take the time to do that, but I just wanted to show you a strategy of how when you're given complex or either complex numbers or just our irrational numbers, a way to go back, which is actually a lot quicker, I think, than writing them out as factors. I hope you feel a little bit better about using your calculator to find rational zeros and being able to find factors, linear factors, zeros, and x-intercepts of a polynomial, and to be able to write a polynomial from given zeros.